Hey, welcome to another video. So we're going to continue talking about some features and properties of some functions. And the next thing we're going to do is we're going to talk about even and odd, an often misunderstood thing or property of functions that students really want to get wrong because they have a misinterpretation of what even versus odd means. And it's right in the root of the word even and odd. So we'll talk about exactly what even and odd means, how to look at it graphically, what that translates to algebraically, and then how to check whether a function is even versus odd. I'll give you a very, very quick way to do this. So number one thing, that when we talk about even versus odd, of course some numbers pop in our head. We know even numbers are numbers like 2, 4, 6, 8, 10. Odd numbers are 1, 3, 5, 7, 9. And so oftentimes what students will do when they hear the word even versus odd is think that that relationship between even numbers and odd numbers is always what determines a function's evenness, oddness, or neitherness. And that's not true. So I'm going to give you the formal definition of what even and odd actually mean. Then we'll talk about algebraically how to deal with it. So what an even function looks like graphically and then algebraically after that. When we say that a function is even, its graph is going to have a certain property to it. The graph of an even function is going to be symmetric. Like if you fold it down the y-axis and fold it onto itself, it would be a mirror image perfectly. We'll talk about what that means algebraically in just a second, but graphically that's what an even function would do. It's going to have a mirror image on right down where that the axis of symmetry, that y-axis, where if you fold it over, it'd make a perfect mirror image. And you can probably look at the graphs behind me and determine which one is even and which ones are odd or not. What odd means, a little bit more difficult. Odd is this symmetry about the origin. So if I rotate the graph 180 degrees, it's going to give me the same, that's kind of cool. If I rotate the graph 180 degrees, it's going to give me the same exact picture. That's what odd means for the graph of a function. Every odd function will have that property, where if we rotate it 180 degrees, it's going to be symmetric. So looking very quickly, we're going to do a couple things here. We're going to look at the graphs and determine even versus odd. We'll also talk about domain and range so you don't forget it. Well, even. Are there any graphs up here that are even? Well, yes. This graph is even. If I fold this across the y-axis, I've tried my best to make this symmetrical about the y. This has symmetry to it. This is an even function because we have this idea of symmetry about the y-axis. If I fold it across, it'd match up. Do we have any odd functions? Well, let's look at the next one. Is this even? Well, no. If I fold this across the y-axis, it's not going to match up. But if I rotate it 180 degrees about the origin, it would still have the same exact picture to it, the same exact graph. This is an even function that's given us this particular graph. This is an odd function that's given us this particular graph. Now notice something. Maybe you had some trig before, but if we start thinking, oh, well, odd just means the power of the function or something like that, that's a trigonometric function. If I use pi, or I've manipulated a little bit, but this is based on a trigonometric function. It's sine of x, sort of. I would use negative pi and pi. But the point is that the exponent itself has very little to do with actually being even or odd. In power functions, it does. Single term functions, the power will tell you whether the function is even or odd. That is true. But if I have polynomials, we really lose that. Also, functions that don't even have exponents can still be even versus odd. So please don't let that misconception, probably the biggest one is even and odd, that misconception that, oh, the exponent is what tells me that it's even or odd. Not necessarily. So cosine of x is an even function, but it doesn't have an exponent at all. We need to get away from that. We need to understand the definitions of what these things mean. Even means, as far as its graph is concerned, that it has symmetry about the y. Odd means, as far as this graph is concerned, it has symmetry about the origin. That needs to be in your head right now. So even, yes. Even, no. But it is odd. If I rotate 180 degrees about the origin, or it has symmetry about the origin, that's an odd function. You know what? Let's skip this one for a second. Let's look at this one. Is that even? Think in your head right now. Is that even? If I fold this across the y-axis, does that match up? No. If I fold it across the y-axis and the x-axis, or rotate it 180 degrees, is it the same picture? Yes. That right there is an odd function. And so you heard me mention something, this double sort of symmetry. If I reflected one piece across the y and then reflected across the x, so all you visual type people, you could probably see that right now. Can you see it right? If I fold this and then fold it again, it would give me the same picture. Same thing here. If I reflected this about the y and then about the x-axis, it's going to give me that same exact picture down here. That is another way we can think of rotating 180 degrees about the origin. This definitely has symmetry about the origin. So symmetry about the y, even. Symmetry about the origin, odd. Symmetry about the origin, odd. Symmetry about the y, no. Symmetry about the origin, if I reflect it twice, does it make the same picture? Or rotate 180? No. That would be neither. So if we want to write this stuff down, this is an even function. Both of these are odd. And this is neither. A lot of graphs are neither even nor odd. I don't want to say most of them, but lots of graphs have this the featureless as far as having any sort of symmetry there, and that's okay. We're just trying to classify this, and where we're going with it, so that you know, is that when we get to graphing polynomials and especially rational functions, the even versus odd is going to tell us a whole lot about how they look in a neighborhood of points. So how they behave with asymptotes, how they behave around x-intercepts, has to do with multiplicity, and that's an even versus an odd idea. So getting the picture of what these look like, incredibly important. That's why we're studying that. Now, before we go back, and I'm going to talk about the algebraic manipulation of this in just a second, but before we do that, I want to make certain that you understand domain. So stick with me here. Let's just go through these really quickly. Do you remember that the domain is the section or interval of the x-axis that our graph covers, and the range is the section or interval of the y-axis our graph covers? So let's run through the domain real fast. Domain here would be from -4 to 4, including the endpoints. Range would be from 0 to 3, including the endpoints. Here, domain is the entirety of the x-axis. It will eventually cover that, -infinity to infinity. Our range, even though we have a couple points here, our range will eventually cover the entire y-axis. This graph goes down forever. It will cover the entire y-axis. Domain would be all real numbers. Range would be all real numbers. Here, domain, this will eventually cover the entire x-axis. Domain is all real numbers. Range is from, not the whole y-axis, but only from 0 and up, but not including the 0. We have parentheses, 0 to infinity. Here our domain is awkward. Man, what can't we get out? If I look at the x-axis only, I can cover everything past 0. I can cover everything up to 0, but 0 itself has no output. Remember, the domain is all the values of x that give us a valid, defined, real number output. 0 doesn't have that. I would have to exclude 0 here. Interval notation, -infinity to 0, and then 0 to infinity with a union between, or just say x cannot equal 0. And that'd be fine. Same exact thing happens on the range. I don't cover the whole y-axis. I cover everything from 0 down, everything from 0 up, but not 0 itself. So I'd exclude 0 in the same exact fashion. I hope that makes sense. I just want to refresh your memory because domain can get lost when we don't really practice it. Now, because I mentioned that even is a symmetry about the y, and odd, the graph will have symmetry about the origin, sometimes we don't have a graph to look at. And I want to be a little bit more specific on what happens with even versus odd, because that is a definition, but not the only one that we have. This is a great definition for looking at graphs and go, oh yeah, even would fold over, have symmetry about a y-axis. Odd would rotate 180 or double flip around x and y, if you want to call it that. It has symmetry about the origin. But I want you to look at what happens to the inputs versus the outputs, and it'll give us a new definition for this. This is more important, so really focus on this. If we look at an even graph, what happens to the outputs when I plug in opposite inputs? And think about how this would cause symmetry here. If I plug in or look at my inputs 4 and the opposite -4, what would have to happen to keep my graph symmetrical about the y? Well, what would have to happen is if I plug in, let's see for you guys, -1 and 1, and I want symmetry about the y-axis, I want to look for even functions. If I plug in 1, -1, and +1, my outputs would have to be exactly the same. If I plugged in -4 and +4, my outputs would have to be the same, no matter whether they're both above or both below. Here's what even really does. Even functions take opposite inputs and give you equal outputs. They give you the same output. They'd say, okay, take two opposite numbers, so -3 and 3, or -4 and 4, or -1 and 1, or whatever you have, and whatever my opposite inputs are, they would have the same output. You have to see how that would create symmetry about the y-axis. That would say, yep, my outputs are the same when my inputs are opposite. That's what even functions really do. It says if I plug in, if I remember to put my sign correctly, if I plug in opposite inputs, they have the same output. Opposite inputs, they have the same. That's 2 output. That is what even functions do. Now, mathematically, here's how it looks. It says if I plug in, man, I hope you get this. If I plug in opposite inputs, notice how this is opposite inputs. It says 3 up, -3. This is -5, oh, -5. Opposite -5, that would be +5. Whatever x is, these are giving you opposite inputs. And it says for even functions, if you have opposite inputs, you will have equal outputs. That is what defines an even function. It says if I'm plugging in 2 numbers which are opposites, my outputs will still be the same. Are you seeing how that would give you symmetry? Opposite inputs, same outputs. That's how we check. So basically what we're going to be doing is we're saying if I take -x, that's the reason why we started evaluating like several videos ago. Like, hey, can you plug in 5? Can you plug in -x? Can you plug in x + 1? Why? Why would we try -x? That's how we show even functions and odd functions. So with even functions, the graphs will be symmetrical about the y, but what that means for us is that if I take opposite inputs, it will have to have the same output out. Opposite inputs will still yield equal outputs. Now, odd is different. Odd says, if I wanted to be odd or symmetric about the origin, I want to be able to plug in opposite inputs, but get opposite outputs. So plug in 1 and -1 and get out 5 and -5, say. I want to be able to plug in 2 and -2 and get out 1 and -1, say. I want to be able to plug in opposite inputs and get opposite outputs out. That would give us this ability to rotate and have the same exact picture, 180 degrees, or about the origin. That's what's happening here. If I take +2 and -2, I'm getting opposite outputs, 1 and -1. Every single odd function will have that feature. Now, how's that look mathematically? Well, if we have symmetry about the origin, if we're talking about odd, this says if I plug in opposite inputs, notice these are opposite inputs, then, well, the outputs would be opposite as well. So it says take your input values, plug them into your function. These things will not be equal. That would be even. If I take out opposite inputs and I get the same output, I'm getting symmetry about the y-axis. If I take opposite inputs and I get opposite outputs, I'm taking opposite values in, I'm getting opposite values out, no matter how you cut it. That would be an odd function. This is what defines odd. So it all comes down to your understanding of what even means and how that relates to it mathematically. You have to get it. If even means symmetry about the y, that requires you to be able to take opposite inputs and get out the same output. Opposite inputs, same output, equal. Odd says, I'm requiring you to take opposite inputs and get opposite outputs. Here's opposite inputs and their opposite outputs. This is exactly how we check algebraically to see whether a function is even or odd. So, surprisingly to some of you, it's not about the powers. This definition works for every function that we would check, even versus odd. Absolute values, those don't really have exponents in them, but they have a power of 1 if you want absolute value x. That v that we get for an absolute value, that's an even function. It has nothing to do with the exponent. Sine, cosine, tangent, those things we can check whether they're even, odd, or neither by taking these in a certain interval of numbers. So we'll be doing that in just a moment. I'll erase these functions. At this point, you need to really have in your head 2 things. Number 1, how to identify even and odd versus the graph, whether it's symmetry about the y, symmetry about the origin, or neither. And then the idea that even means opposite inputs, same output. Odd means opposite inputs, opposite outputs. And that's going to really drive what we do in just a little bit. So stick around, I'll be right back. Okay, little mistake there. What I want to mention is that when we have f of negative x, we plug in opposite inputs. I had this sign wrong. This sign should be over here. That should be an opposite output. So this says, hey, if I take opposite inputs, my outputs are also opposite. Sorry about that. I want to make sure that that is clear. The sign's going to be wrong in just a little bit, but this is what you need to know. I need to make certain that's clear for you. So odd says, if I plug in opposite inputs, I've got opposite outputs. This is the output of the function. This is the output of the function. They would be opposite values. So that's what odd means mathematically. All right, so we're ready to see whether these functions are even, odd, or neither. And instead of graphing, because it takes a whole lot of work, we're going to use the definitions of what even and odd actually mean. So even means if I plug in opposite inputs, I'm going to have the same output. Odd means if I plug in opposite inputs, I'm going to have opposite outputs. That would give us symmetry about the y and the origin respectively. So one way to do this, it's not by looking at the exponent all the time. It leads us down a really bad path. There's sometimes I'm going to show you very quickly how to do something very similar to that by looking at exponents and changing certain parts of it. But in general, one idea to find this without graphing it is to just evaluate it. So if we evaluate our function from negative x, and we get exactly the same thing. So basically, we plug in negative x and see if we get the same function back. If that's true, if we plug in negative x, evaluate for negative x, and the thing we got out here is exactly the same thing that we started with, that is what you're starting with, then we have an even function. It says you plugged in opposite values in general, not for just one point, and it gave you the same outputs. It gave you equal outputs. That's even. For odd, we could do the same thing. So if we plug in negative x to our function, and we get out the same thing we started with, but with a negative sign, or every sign is opposite, that would be odd. So in general, we're going to evaluate for negative x and see what happens. So you can have maybe a guess at what goes on with some of these. You go, well, every power is even. It's probably even. That's true. Sometimes you can do that. Every power is odd. It's probably odd. No, it's not. That's not odd. There's even and odd. Let's go, wow, what in the world's that one? The idea isn't just about exponents. The idea is what happens when I plug in opposite inputs. So I'm going to show you how to do that with these 6 examples. So just walk through them and show you what we're looking for. I'm also going to give you kind of a shortcut here. Mathematically, what we're doing when we evaluate for negative x is we are plugging in an opposite input to our original function. We're saying, imagine taking positive numbers and plugging all negatives, or negative numbers and the opposite of negatives, positives, and seeing what that gives us case by case. So, but for all inputs. If I do that, man, our knowledge of compositions or of evaluating functions comes into play. We've already done this. We say, how do you evaluate? Well, you say, I want to replace the x with something. I want to create a blank space. I want to plug that negative x in there for that blank space. What is going to happen when you have even exponents? Well, the powers aren't going to change. The signs aren't going to change. The signs are all going to be positive. So if we have these positive even exponents and we start plugging in negative numbers, it's going to always give us positive out. So for every positive whole number even power, we're always going to be getting positive numbers out. So negative x to the 4th power has to give you positive x to the 4th. Our sign's not going to change. Our minus isn't going to change. Negative x to the 2nd power is positive x squared. Notice how what we got out is exactly the same thing as what we started with. So this says you plug in opposite inputs, you're getting the same exact outputs out, no matter what input that is. That right there is the definition of even. It says if nothing changes, when you plug in a negative x, you evaluate that, nothing changes, you have an even function. Now, let's try g of x. When we look at that, we go, right, you know what? We know what to do. We know that in order to test whether this is even, odd, or neither, we start by evaluating negative x. We start by plugging in a negative or an opposite number and seeing if we have the same outputs or opposite outputs. So we're going to do this and go, all right, well, when we evaluate things, we always give ourselves some blank spaces, and then we plug in whatever value is here. So this says replace your x with negative x. No problem. Here's negative x. Here's negative x. We've already looked at compositions. Well, with our power 2, we know that even powers, they give us positives all the time. They maintain positivity. So we would have an x squared minus 1. our denominator has not changed. But our numerator, there's no even power here. It's an odd power. It's actually a power 1. Well, odds maintain signs. So that would be a negative x over positive x squared minus 1. If I wanted to rewrite it just a little bit, I could write that negative in front. That is saying, hey, look, you ended with the same thing as you started with, but with a negative in front. That's this case. That says you ended with the same thing. Hey, look, you plugged in negative x. We plugged in negative x. You got the same exact thing, but with a negative in front. Same exact thing as you started with, but with a negative in front. This is what odd looks like. That's what odd looks like. So, in general, even's a little bit easier to find because nothing changes. You go, oh yeah, nothing changes, stays the same. But odd is a little more difficult because you have to find a function where if you factor a negative out, you can get the original function with a negative in front. That's what we're looking for. Let's talk about one more, and then I'll give you kind of a quick way to deal with it. So h of negative x. This is testing whether we have an even, odd, or neither function. And so what this says is you're going to replace your x value with something, but notice how the plus 5 cannot possibly change. You go, all right, let's evaluate with negative x. I know that odd powers maintain signs, so this would be negative 3x to the third. Here's negative x cubed. 3 times that's negative 3x to the third plus 5. And you go, well, that's not exactly the same as that. Notice this is not the same thing as that. So it can't be even. So you go, okay, what's the next step? Well, let's factor out a negative. If I factor out a negative, I get 3x cubed minus 5. Watch the minus 5 when you factor that negative out. You go, well, wait a minute. This is not the same thing as I started with. So this is not just opposite outputs. This is not the same output at all. Right there, that's telling you that this is neither. It's not even, you didn't get the same thing out. It's not odd, you didn't get the same thing with a negative in front. You didn't get the original function with a negative in front. You got neither the original function in either of these cases. So you factored a negative, that's not the original function. You didn't factor a negative, that's not the original function. So this is not even, not the same. This is not odd, not the same with a negative factored out. This would be neither. Now what we can infer from that is that this doesn't have any sort of symmetry about the y-axis or about the origin. So it's kind of nice to know that. Now here's the little shortcut that I would do. When I do these on my own, I know that because even powers make everything positive and odd powers change the sign if I plug in a negative and constants don't change, how I check for even, odd, or neither is I just change the sign of my odd powers, and then if I get the same thing out, well, then I know it's even. If I don't, well, then I know if I get an opposite in front, then I know it's odd. If I get neither of those two things, I know it's neither. So here I say, hey, let's change my odd powers. There's none. Okay, that's even. Change my odd powers. Okay, there's one odd power. It's power 1. So I'm going to change that sign. There we go. Okay, factor that's odd. I'm going to change my odd powers. So I change that to a negative. So change the terms of my odd powers. Leave my constants. Oh, wait, that's neither. So that's a very quick way to at least check your work with it. Let's go to the next one. So if I think about that, if I think, let's plug in negative x, my odd powered terms would change signs. I don't have any. Nothing can possibly change signs here. That's an even function. Are you seeing what I'm talking about now? So I'm looking at this and going, my odd powers would change signs if I did f of negative x. I don't have any odd powered terms. And so I know that x squared would stay the same, plus 3, that's a constant, it can't change. X squared would stay the same, minus 1 would stay the same. That's exactly the same function I started with. Even though I plug in negative x, that would be an even function. And this function will be symmetric about the y-axis. Important stuff to know. I'm going to jump down here for a second. So h of negative x. H of negative x. I go, all right, let's see. I'm going to change my odd powered terms. I'm going to leave my even powered terms alone and my constant alone. That's what negative x would do. Now, can you show this by evaluating? Of course, I've shown you 3 examples where that's the case. I'm going to show you another one right here. But if you're really thinking about it, what would happen is our even powered terms would not change signs even if I plug in a negative. My constants cannot change at all no matter what I plug in. My odd powered terms will change signs. So negative x cubed would become positive x cubed. You go, wait a minute, I can't factor a negative out of that. That's true, but think further than what we're doing. This is why we talked a long time about the idea of you're plugging in opposite inputs, you're getting out opposite outputs. I don't really care that I don't have a double negative here or something. What I care about is that this really is probably appropriately written as this. Here's your input, here's the output. Here's your input, here's the output. I have opposite inputs. Do I have opposite outputs? Yes. One has a negative in front and one does not. This would be an odd function. This is going to have symmetry. Its graph is going to have symmetry about the origin. If you need to see it another way or you want to show some more work, let's say, we'd have to show that we'd be plugging in this to here. I'm going to erase this for a second. I'm going to do it that way. We'd say, all right, you have a negative. I know that I'm replacing x with negative x. I'm plugging in opposite inputs. I know that negative x cubed is negative x cubed, but then that negative is going to give me positive x cubed. This would be positive 3x squared because even powers always make that positive for you. Or if you want to show this differently, say, hey, you know what? I can factor that negative. I can leave this as negative x cubed over 3x squared minus 9. Then you do that. Move this negative to the front of your fraction, leave this negative as negative x cubed, and now you can really see that, hey, here's the original that I had. Here's an opposite in front of it. So opposite inputs yielded opposite of the same exact output that we had. Either way you want to go on that one. Now the last, so this is definitely odd. The last one. So we know that even and odd, we take an opposite input. So we evaluate for negative x. And we look at what happens. If we get the same thing out, even, if we get opposite outputs out, so the same thing with a negative in front, we get odd. Now, if we run in a situation like this, where you go, all right, well, wait a minute. If these are positive numbers, because domain-wise, you'd have to have positives to give you a real defined output, then these will all be negatives. If these are negatives, that would be defined, and those would be positive. So one of these is not a great situation for us. When that happens, you have a neither. Because if your positive values are defined and your negative values aren't, what that means is you plug in opposite inputs, and one of them works, and one of them goes, not real number. When that happens, you have a neither. This is not even. There's no symmetry about the y. It's not odd. There's no symmetry about the origin. This graph will have no symmetry at all because opposite values aren't even defined. These would be imaginary numbers. So we say neither. All right, I hope that makes sense for you. I hope that graphically you understand the idea of symmetry. I hope that you understand why this is the case based on that symmetry and looking at the graph. So then we used it. We understand that even means opposite inputs, same exact outputs. Odd means opposite inputs, and then opposite outputs yielded from that. We can check it through evaluation, simplifying if we get the same exact thing we started with by plugging in negative x, we have an even function. If we get an odd function, that means that we have a negative that we can factor out. We have an opposite in front of the original function after plugging in negative x. If those things don't happen, then you have a neither. So that's it for even and odd. We'll talk about some extrema next time. Local extrema and absolute extrema. So local maximum or relative maximum and absolute maximum. I'll see you for the next video. Have a good day.